All right. Thank you, folks. Thank you for coming here. My name is David Ye. I'm the Senior Product Line Manager for OTN market segments. Today here, I want to take this opportunity to introduce you, essentially a FPGA-based solution to build essentially a 500 gig or even 1 terabit OTN line card. I think, through this presentation, you will. If I do my job correctly, I'm hoping that you can, realize how powerful the FPGA is today, and of course, because of the programmability, that will enable you to be essentially ready for future network technologies, as well as build your own differentiations. Okay. Okay, so this is a picture of the optical network that is quite known to all of us. Of course, at the top you see the core network, and then you have the metro edge or metro long haul. I think currently in the metro, people are differentiating between the so-called metro long haul, metro edge, and then at the bottom you actually have the actual enterprise network, as well as wireless infrastructure, and now the emerging data center. Okay. So because of the need for, or the desire to have essentially a common platform to ease the OAMPs, we're seeing actually OTN being the protocol that is starting to really proliferating down to enterprise, as well as the wireless, as well as the data center. Okay. So in addition to OTN proliferation, it's known to everybody here. Okay, we're no longer talking about 10 gig. We're talking about 100 gig and beyond. Okay, so speed is increasing everywhere, not only the core, but as well as the edge. And on top of the speed increase, there's also architectural change that we're seeing here. Of course, in the core, we're starting to see OTN switching being a very dominant requirement, and of course the rise of the packet optical transport system, or some people refer them as hybrid switching. So that's essentially a packet-based plus OTN switching capability all in one chassis. We're starting to see that as also very important in metro as well. So there seems to be a common theme going on within our network, but if you look at all the different requirements, or essentially what are the problems that both as a system vendor or as a chip vendor, the problem that we're trying to solve, it's actually quite complex. Okay. So I took a picture from Andrew from Informatic, and if you see the middle picture with the OTN switching plus the optical OTN transport and the OTN muxponder, so that's the picture that Andrew has been showing for quite some time. But I essentially try to add additional requirements on top of it, and if you see the packet optical transport system. So that's essentially a bigger circle that is, including the OTN switching as well as our traditional transport and muxponders. And next to it, I mentioned about data center interconnect. There is essentially a need to interconnect two data centers. It's quite obvious. And so sometimes the data center could be further apart. So as everybody know, OTN offers essentially a framing that allow you to provision as well as doing performance monitoring. But I think more importantly for data center is the FVC, and plus for 100 gig, because of our coherent technology, we can actually achieve a certain reach. But for data center interconnect, the requirement for OTN, it's slightly different from the traditional transport or the service provider requirements. Okay, obviously density, low power, and the incumbent providers, those guys want to turn up service very, very quickly. Definitely not in the matter of months. Even in days is considered long. So I think essentially the requirement is very different. And then if you look at what is outside of all these big circles, those are the evolving technology that is at the moment currently not being standardized. So how do people actually build systems around all these requirements? And so I would actually essentially present to you that I think based on with an FPGA, I think you will have the flexibility to support multiple requirements and really make your differentiation. I think a lot of folks probably has been following Xilinx for some time, and I think Gio Garcia, who is the presenter right before me, also touch on one of our leading device that is so-called UltraScale Plus, that is in 16 nanometer, that will come out essentially at the end of this year. But you can use the current Vertex 7 to build a pretty traditional transponder, muxponder, and it's capable of supporting 100 gig already. Okay. And moving to the left, in 20 nanometer, you really can get the bandwidth that you want, or density that you want. So for 500 gig, in a later slide, I will show you, with 20 nanometer device, you can actually use essentially a single device to achieve 500 gig. And for secret over OTN, because of the multi-ray and low power and lower cost, the cost pressure for that kind of application it's definitely higher. And for those reasons, actually, Kintex will be essentially a very good part to target. So I think I have mentioned about this, but I'd really like to reiterate one more time. It's I think all of us would really, in addition to be essentially market technology leader, I think we all like to essentially really make monies, and I think time to market is very important. Differentiation is also very important, and I think also flexibility. Okay, and I think traditionally FPGA, people always concerned about power and size and cost. I think today the message I want to tell you is I think a lot of those barriers are now pretty much gone. So I do want you to have that kind of mindset now. So here is an introduction to essentially a single chip 500 gig solution. You might see, well, there are actually two devices on this slide, but the story here is with the 20 nanometer device showing on the left here, okay? This device is actually ideal for transponder, muxponder, and OTN switching, okay? And the device on the right, it actually can also support packet optical transport, okay? So I think if I were to give you one key difference between these two in terms of application is the packet support, okay? Because of the what we call URAM, essentially this is essentially memory integrated into essentially essentially a FPGA. You will be able to support packets, packet switching, packet buffering. The actual buffering will not be done in our device, but I should say it's the buffering that can be done in the FPGA. Okay. And the beauty is the two devices, because of our planning, the two devices are or will be pin-to-pin compatible, okay? And from schedule point of view, they are essentially only different by about 12 months, okay? So you can actually starting to design today, and in about 12 months from now, just change your BOM, and you will have essentially a packet-capable line card, okay? I don't want to go through every single needy feature here, but I think here are the key features that you need to remember. Okay, traditionally, transceiver is another sticking point about whether FPGA can support 25 gig IOs, whether you can drive backplane. Okay, And all those answers are yes today. Okay, we have actually the best-in-class SerDes. It's capable of driving, backplanes, 35 dB of loss, tens of taps of DFE. Okay, and then if you look at OTN IP. Okay, so I think traditionally FPGA. Okay, we're selling silicons. So how do I enable, OTN applications? So within Xilinx, we have built up a very comprehensive OTN IPs. Okay, not only as essentially IP blocks, but we are also building subsystems as well as applications. Okay, and moving to 16 nanometer, we have a lot of IP blocks actually been hardened. Okay. So you won't need to use logic resource to build those. Those are just like ASICs or ASSP functions. And if you look at what those are, we're talking about tremendous number of 100 gig MAC, 150 gig interlocken, and you can actually use a little bit of soft logic to glue them to form essentially a 300 gig interlocken. And also the BJ effect for 100 gig SR4 support, and of course there's also essentially a PCS alignment block that we currently use to build the GMP mapper. So those are actually it's essentially hardened blocks inside our device. So I'm going to go through 3 user cases. They are a little bit quite detailed if you look at the slide here. But I just at a very big, I'll make sure I start from the very, very high level. Okay, so for an OTN switching, 5 times 100 gig, so this would be essentially a 500 gig per slot solution. Of course, on the front panel, you'll see here, it's got 500 gig coherent module. Whether it's ACO or it's DCO, that really that's not the focus of this discussion here. So from the OTN framework point of view, if you are going with essentially an ASSP device that is available also just very recently, you actually need to put down 3 devices. Okay, and as everybody know, to develop ASSP, I need to essentially sink almost $100 million to develop an ASSP, and it takes time, and it also takes a number of spin to get it right. And yes, I need to get every single feature into that ASSP. However, with FPGA, you actually have that flexibility. You are dictating what you need. You don't need to rely on ASSP guys to make sure every single feature is in that single piece of silicon. So here, for example, we are not talking about packet switching. Okay, here we only need OTN at ODU level switching. Okay, so this is one case where if you use silicon available today from Xilinx, okay, you will get essentially a single chip. So overall, your board size can be a lot smaller, and overall, your power will be lower as well. Okay. So the key here is 1 chip versus three chip, and obviously I think the one of all the detailed features are highlighted here. All the IOs, even though I'm showing just this is what sometimes people call Gen 1 CF modules, essentially with OTL 4.10, but the IOs are actually also 28 gig capable. Okay, so currently I'm showing essentially a line side facing card, but if you have a 100 gig Ethernet client facing card, you can actually have a direct QXP28 or CFP4 direct connection to our device. Okay, so now let's look at a little bit more complex requirements. Okay, this is the part that actually has the packet switching. Okay, or sometimes people are referring to as GFP. I need GFP multi-channel GFP mappers to support packets coming from the backplane, as well as I need the OTN SAW function to support OTN switching. Ultimately, ASP guys are really designed their device to target this application. Okay, but here what I'm showing you is essentially about 12 months from today, we can actually offer you a chip that actually can do everything that the ASSP guys can do, and it's actually again a single chip. Okay, so as you can see here, you will still have you will have your essentially the OTN SAW functions, and now because of our integrated memory, okay, now I can finally buffer our the packets to implement the GFP, the multi-channel GFP. Okay, before essentially a big block of memories that is available in the 16 nanometer device, you will probably need to deal with smaller distributed memory, and that will cause a lot of hard time to try to close timings. But now with with the embedded, we call it ERAM, you won't encounter that kind of problem. Okay. So now moving on to the data center interconnect. Okay. I'm sure a lot of folks actually see the Facebook six-pack. And it's all well known, right? It's 40 gig today, but I think eventually that will upgrade to 100 gig. And with 100 gig, then I guess you can guess that people will be talking about 3.2 terabits. So the question is, can I actually have OTN interface on all those 32 100 gig ports? And with ASSP today, I think it's almost impossible to realize that. Okay, but with actually FPGA, okay, the 20 nanometer device that is available now, okay, it's two devices. Okay, it's not bad. You can achieve 3.2 terabit of OTN, but I think the story is even better. About 12 months from now, you will have a single device solution. And remember, even though this is not a great example to show the pin-to-pin compatibility upgrade path. But just keep in mind, between our 20 to 16 nanometer product offerings, there is actually a pin-to-pin compatibility. And for DCI, you might challenge me, hey David, DCI from OTN perspective, all the requirements are very simple. Just give me 100 gig Ethernet and just map it into an OTU4 and then send it out, and I'm going to use coherent anyway, or some kind of silicon photonics optics. From framer point of view, it's very simple. But I think I would also point out that it actually is on one of my earlier slides. In the Ethernet domain, there's a lot of new things going on. For example, the one I want to mention is flexible Ethernet. Okay, and I think data center folks. I think there's a presentation given by folks from Google today. With FPGA, essentially it allows you. It has you will have that flexibility to upgrade your design to be flexi capable. Okay, so I think that's one thing to remember. Okay, so all these are so far. All these are just slides, but I want to mention to you that on the floor here today, we actually have a demo. It's on a 20 nanometer device, but because of the smaller logic cell, it's only showing 200 gig, okay? But in the same family, so this is, if you look at the product portfolio, this currently what we're showing is with a VU095, okay? It's 200 gig capable, and it's capable of doing OTN switching. That's what we're showing on the floor, and very soon, actually, in a matter of a couple of months, you will actually get a device. It's within the same family, but it actually has a lot more fabrics, and you will be able to, essentially instantiate the same design and to 5 times Okay, so essentially we are ready. Okay, we're ready to support a 500 gig design. So I think that's pretty much all the contents of my presentation. Here are just some key takeaways. Okay, FPGA is ideal for OTN. Okay, ASSP vendors, as a lot of you folks know, I think ASSP offerings are getting smaller and smaller. You can only get it from probably one guy right now, but FPGA, we are going to stay. Okay, we are offering a platform not only for OTN but as well as for all the other applications. But it's amazing that FPGA has grown so big that we can support 500 gig with 144, 32, actually 33 gig capable IOs, and this is something I think you should keep in mind. And if you just remember what I keep mentioning, right? So we got the best in class SerDes, we got the URAM, and we got this hardened core. And I think what we really want to achieve is to allow you to make differentiations. Okay, but with ASSP that's going to be quite difficult. Okay, and I think we're willing to work with you guys to try to figure out whether differentiation needs to be realized by you or by us. And I think FPGA underneath is the enabler for that kind of programmability and differentiation. Last but not least, I will just give you a slide. Hey, does anybody actually want a white box OTN 6-pack? Okay, and I think FPGA is the enabler for that. Okay, you can actually download different images, or you can use partial reconfigurations, and you can essentially have so-called whether it's line facing or client facing, or you can support different kind of traffic, whether it's fiber channel, Ethernet, whether it's client optics or color optics. Okay? I think that's it. And please come by our booth, and we have some very technical folks there. We can walk you through, hey, what are the OTN multiplexing that we have implemented. It's quite amazing that what we can do with FPGA these days. Okay, great.